Hello, and welcome to another episode of Baz Codes. I'm your host, Codes. Oh no, wait, I'm Baz. Right? Hey, nice to see you. Um, so I've been working on GSSquared's Apple II speaker emulation. GSSquared, of course, is my Apple II emulator project. Currently at 2 plus level. Hopefully soon to make the jump to 2E. I'll start working on that here shortly, and ultimately 2C, GS, and maybe Apple III if I get to it before I turn 100. Uh, so I've been working on the speaker emulation. For a while, I knew there was something wrong with it, and I tried various things without success. This weekend, I dove back into it, see if I could hammer it out. You walk away, you let things percolate, you come back and hammer on it for a while. It's the programmer's oldest trick in the book, letting your subconscious just uh, work on problems while you're doing other things. It's true. It's a real thing. Raise your hand if that happens to you. Yeah. Okay. Uh, so, just to give you some points of reference. First off, um, here's the bad sound that I was getting. Okay, it's about the right pitch, but you can hear it's like garbly, a little bit distorted, right? It's not at all the clean, classic Apple II sound that I remember. So let's talk about a couple of terms real quick: cycles and samples. Cycles, of course, refers to the 6502 processor cycles. Um, tick tock of the clock. Every instruction takes a few cycles, anywhere from 2 to 7, I think. Um, and whenever the processor hits that address C030 speaker toggle, the speaker cone goes from low to high or from high to low. It'll actually physically push the speaker one way or the other whenever you hit that soft switch. And if you toggle the speaker, if you hit that thing at the right frequency, you'll get tones out. Uh, Now, in theory, you can toggle the speaker at best maybe every 4 cycles. And yes, there's an exception to this, and I'm sure you can tell me what it is in the comments. So 4 cycles to high, 4 cycles to low, 8 cycles total per 8 CPU cycles per audio cycle gets you the ability to generate an audio stream at like something like 120 kilohertz, way above human hearing. Uh, in theory, I'm not sure the speaker cone can physically move that fast, so that's probably the limiting factor. Um, but you can go way over. I think you can go over 20 kilohertz without too much trouble. Now, uh, and there is a technique, though, called pulse code modulation that's used on the Apple IIs that does hit the speaker toggle at extremely high rates in order to simulate multi voice sounds. Two things: it's like playing 2 or 4 tones at the same time, and also a technique where you play back essentially digitized audio, like a digital recording. Um, Now it's not clean like a modern sound system, but back in the 1980s, it was pretty amazing, and all just from whacking uh, this speaker cone toggle, literally telling the speaker cone to move in or out. So I'll have more on that later. Now samples. Sorry, that was long-winded about cycles. Samples is how many data elements or numbers per second you use to describe your sound output in a modern computer sound system. Modern computers emit sound using a very accurate stream of numbers that precisely locate the speaker cone. Note on the Apple II, it's either in or out, right? You got you have 1 bit. You have basically 1 bit of resolution. On modern computers, they can be accurate to 16 or or more bits. I don't know the specific specs, but obviously it's good enough to represent, CD quality audio, high quality stuff. So I spent like 8 hours looking over the algorithm in my code and trying various things, and then it hit me. So my old code was calculating a number of cycles per sample as an integer in one spot, but there was always a fractional component left over. So this is a math thing, and it was a subtle math thing. In short, the samples didn't divide evenly into cycles, and so I had these fractions left over that weren't being taken into account. And that's what is creating this distortion right here. So after modifying my code and changing how I set up the sound library so that all these numbers were evenly divisible, now all of a sudden I was able to get, if I can find it, yeah, here we go, this. This result. And that's way better. That's the beep I remember. So I was really happy about that. That was the moment of epiphany. There was still another issue though. So whenever you're doing in audio processing, signal processing, whenever you're doing downsampling, and that's what this process is. We're basically taking 1 million, well, up to 1 million, 250,000, 120,000, whatever the number is, of samples of, are we pushing the speaker cone in or out that the Apple II can generate through its little 1-bit mechanism. And if you're taking that down to 44,000 roughly samples per second, you're downsampling, right? So you're taking a larger number of samples and creating a smaller number of samples over it. You can create audio artifacts. It's just a part of the process. And these will often exhibit as noise or super high-pitched whine, like high frequency, 15, 20 kilohertz whine. Very annoying and distracting. Especially when you're playing the pulse code modulated sounds I mentioned before. So I'm going to give you an example of this in the Virtual 2 emulator. We've got a neat little program here called Time Lord, which is I think it's multiple tones at the same time. It's going to be like a kind of like a beatbox or 80s type synthesizer, but it's pretty cool. Wait, no, come back. Thank you. Okay, so we're going to run the program here. Output to speaker, and I'm hoping this will catch the artifacts because they're pretty dramatic. Loading. There we go. Okay. So turn that up a bit. Yeah, can you hear that? It's a fuzz. Whine. Sorry, Virtual 2. I have just the eval version of it, and it decided to take this moment to pause the emulator. So I'm going to go ahead and move on to showing this in GS2. Now, like I said, that this noise introduction is a normal part of downsampling, but to correct for this, you can apply low-pass frequency filters. And what that's basically saying is you've got all these frequencies that make up your sound. You're just cutting out ones outside the range that you're interested in. So here's this. I'm going to go ahead and boot. I put too many Control G's on the command line there. It didn't like it. Okay. Oops. Did the wrong thing there. There we go. Okay. So we'll go ahead and fire up Time Lord in GSSquared. Yeah, we spent a lot of time waiting for floppy disks, didn't we, back in the day? So as you can tell, there's no noise and no whine. If there is, my old ears can't hear it. I have done some signal analysis on the waveform results. It looks pretty clean. Maybe some of you younger folks out there can tell me if you're hearing any artifacts, but definitely a lot better than the Virtual 2 example, right? And I'm doing this by doing this filtering both on the input and on the output side. So the raw samples are being filtered to get rid of samples that you can't hear. You know, I mentioned in theory you can drive the Apple II speaker at way over 20 kilohertz. Well, there's no point in trying to represent that. It's going to get played out your computer speakers at no more than 20 kilohertz. So first we are filtering that to clean that up. And then after downsampling, we filter again, because each of these steps can create aliases or artifacts. I'll stop that. So again, in case you didn't hear that, we pre-filter and post-filter through this process. And anyway, I think that's sounding pretty good. My acid test here was when I fired up this guy. It kind of blew me away how clean and cool it sounded. Now there's a vibe to this, and that's intentional in Karateka. All right, there we go. Sorry, I put it into accelerated mode for a minute to boot faster. And I don't know what it's doing now. That sounds great. I hope you'll agree. And if you liked this little jaunt into signal processing, make sure to like and subscribe. You know you're gonna, because you're a good person, and that's just what good people do. They like and subscribe. Have a good one.